All right, let's talk about hemiacetals and carbohydrates. Before we get into carbohydrate structure and how this relates to hemiacetals and acetals and what does that have to do with anything, let's just talk about that. Let's just review the way that a hemi or acetal gets formed. So here's the generic formula, meaning we don't have our groups in, we just have kind of a focus on the functional group. So the formation of a hemiacetal is represented right here in this first half. So we have an aldehyde or a ketone reacting with an alcohol to get a hemi. And so hemi means half, right? Half. And so a hemiacetal is half an acetal. And we'll kind of talk about what half are we talking about. So an aldehyde or ketone, now this portion, if you look really closely at the pattern of this part of the reaction, of the aldehyde or ketone reacting with the alcohol in an acidic environment, you may recognize the mechanism by which it seems to occur, the pattern, if you will, by which it occurs is familiar. It is an addition reaction, which we've seen in many places in our quarters so far. So for example, when we were first introduced to them, we were talking a lot about alkenes. We had a carbon double bonded to a carbon, and we might react it with something like, say, water. And we have, and this is kind of my generic way I talk about it is, like, okay, we lose the double bond, like I think of it as like a drawbridge, and it opens up, and that creates the two jazz hands, which I really just mean like some, a place for a new single bond to occur instead of this double bond. And one jazz hand will grab one part of it and one jazz hand grabs the other, and whatever we form depends on what is here to grab. So this would be a hydration reaction. That's really similar to what happens here. So if we look at the mechanism of how the pattern of this turning into this, we had to, let's first note there's a lack of a double bond. So let's lose the double bond. Let's open up then, we're going to get our jazz hands. If you want, you can think of a hand there. But essentially, we still need this carbon to be bonded to four things. And this oxygen, you may remember that the oxygen does have these two lone pairs. We have a tendency to not draw, to also have 8 valence electrons. So jazz hands, the oxygen grabs the hydrogen, and that's what creates this hydroxyl group right here. And the carbon grabs what's left of the alcohol, the oxygen single bonded to the carbon group. So if it helps to think of a specific alcohol, this could be methanol. The hydrogen went here, and then this is OCH3. So it's going to grab this portion, the alkoxy portion, oxygen single bonded to the rest of the organic molecule, and you see that here. That's what this portion is right there. So that occurred by an addition reaction. And if that once you understand the pattern of an addition reaction, then you can apply that concept of we're going to lose the single bond and we're going to grab. It's just remembering what grabs what. The hydrogen goes on here to make this hydroxyl group. The alkoxy group goes on to what was the carbonyl carbon, and then we get this little carbon alkoxy group right here. Now this portion does not occur by addition, because we don't have a double bond to add across. Looks a lot more like substitution. We're going to substitute something off. And what we're substituting off is going to be this hydroxyl group. So it's going to leave. So substitution reaction. And it goes with the hydrogen, and that's how we get this water over here. So the hydrogen from the alcohol and the hydroxyl group from our hemiacetal. And nothing happens here at this little alkoxy group we already added. Instead, we're going to substitute this alkoxy group from the alcohol. This could be the same alcohol as here or a different one. We're going to replace it, and then we have that group then up here. So if you notice, this acetal has two of these OR groups, these two alkoxy groups. 2 alkoxy groups. Remember, alkoxy means alkyl, meaning it has a carbon or at least one carbon, and then oxy, it's single bonded directly to an oxygen atom. So 2 alkoxy groups. And that's what a hemi is half of in terms of the acetal. It only has 1 alkoxy group. 1 alkoxy and 1 hydroxyl. And that's what makes it half. Now, in general, the acetal form is more stable than the hemi, but we're going to talk about an exception to that in just a moment. Something to remember if you're looking at problems that are asking you to identify if something is a hemiacetal or if something is an acetal, is remember that for it to be a hemi, these 2 groups have to be bonded to the same carbon. Having a hydroxyl group just anywhere in the molecule and having an alkoxy group just anywhere in the molecule does not make you a hemiacetal. Those 2 need to be bonded directly to the same carbon, and that's true then of this acetal too. Having 2 alkoxy groups doesn't make you an acetal. They have to also be bonded to the same carbon. So, what does this have to do with carbohydrates? Well, I'm going to bring up this hemiacetal portion, the making of a hemiacetal. I left that up there so that we can kind of reference it. So, a hemiacetal starts with an aldehyde or ketone, and that's important to remember what functional groups how do we prepare a hemi or any functional group? Where do we start? So this is aldehyde or ketone, and then this is an alcohol. Well, our carbohydrates, if we think of the simplest form of carbohydrates, which are our monosaccharides, our simplest sugars, those, for example, glucose. Now, if you've seen glucose before, you probably see it in the cyclic structure, because that's the one it's the most stable in solution, but it also will exist in this linear form as well, this linear form. So these are essentially tautomers of each other, where they can interconvert between. And you may notice that in this linear form, our glucose has an aldehyde right here and many alcohol groups, but this is really the one of interest right here. But essentially we have within one molecule the components that could chemically react together to make a hemiacetal. And so you can have what's like it's an intramolecular chemical reaction. That means within the molecule, the one molecule, we have it. Oops, sorry about that. So when this reaction occurs is when the linear monosaccharide will cycle up, is how I call it. That's not a scientific term, I'm sure. Make sure my pen's still working, sorry. So this molecule can kind of fold over and we get a reaction between the aldehyde group and the alcohol group. And then look here over then in this structure. So looking here at this carbon 1. So you'll notice we've lost the carbonyl carbon. But this carbon right here is a hemi. It's a hemiacetal carbon. And if you're not sure, look, directly attached to it is a hydroxyl group. There's the important hydroxyl group. And also directly attached to the same carbon is an alkoxy group. This is an OR group. The fact that it cycles all around doesn't really matter. So our monosaccharides, which are the monomers of carbohydrates, in their cyclic form are held together by a hemiacetal linkage. They link. The chemical reaction that gets them into their cyclic form is this addition reaction across to the double bond to go from having an aldehyde functional group to having a hemiacetal functional group. And actually, in a cyclic form, the hemiacetal form is much more stable. And so in terms of the equilibrium, we get an equilibrium between the cyclic form and the linear form in solution. The cyclic form is favored by equilibrium and is going to be more common. So what about more complex carbohydrates though? Because we know that our monosaccharides like fructose and galactose and glucose are not our only carbohydrates. Well, that still relates as well. So in looking at then an acetal is created by a hemi reacting further with another alcohol or the same one, so an alcohol again, in a substitution reaction to substitute the alkoxy for the hydroxyl group. So let's look at these two monosaccharides. We have glucose and galactose right here. So when I get these molecules near each other, think of this darkened carbon here, and you can recognize it's a hemiacetal, carbon directly attached to a hydroxyl group and also directly attached to an alkoxy group. So right here we have a hemi, so hemi. And over here, in this molecule, we also have a hemi way over here, but we also have what is essentially an alcohol group, an ROH right there. What that means is we have an opportunity for these two molecules. We have chemically compatible functional groups that can react together. So when we form lactose, which is a disaccharide, two monosaccharides chemically joined together, they join together through the making of an acetal, through an acetal linkage. Now we happen to call it a glycosidic bond or the glycosidic linkage, but that's really just a term that means like a covalent bond between a sugar molecule and something else. So this is a sugar molecule and another sugar molecule, but it is actually an acetal linkage. And let's look at why. Here's our carbon. There's our carbon that previously was an aldehyde and then became a hemiacetal as it went into its cyclic structure. This carbon is bonded to an OR group. Remember, this is a carbon, so this is an OR group. That's an alkoxy group on this side and an alkoxy group on that side. So this here is our little acetal carbon. And this glycosidic bond is also an acetal linkage, so it's an acetal. And this actually locks the ring when it does this, so it no longer, this particular side of the molecule can no longer open up into that linear form. This side actually still can because it has this is a hemi still over here. And we're going to kind of come back to that when we talk about reducing sugars much later in the quarter on why some disaccharides can still have a positive reaction and be reducing sugars and some cannot. Now, what about then our polysaccharides like, starch and cellulose and glycogen? So our polysaccharides, where we bond many monosaccharides together, are just repeating this on. So then this hemi could react further, and it would have a hemi on one side that could react further. And so we get these complex sugar molecules, whether for storage or structure, like cellulose, that are linked, these glucose molecules in particular, though they could be other monosaccharides, linked together over and over and over through the chemistry that we're seeing up here. This substitution reaction that takes us from a hemi to a full-on, a hemiacetal to an all-the-way acetal, because we have multiple compatible functional groups in one organic compound.